Thank you. Hi, everyone. I'm Maryam Fazel from University of Washington, and I want to first start by thanking all the organizers. It's been a really cool workshop and boot camp so far. So yeah, thanks for organizing and inviting me. I'll be talking about the problem of linear quadratic regulator in control. It's actually nice that a lot already talked about very similar problems, and he set up with applications and motivations and so on. So I'll skip the most of the motivation part. What I'll talk about is joint work with some great collaborators I was very, very lucky to work with on this project. Ron Gil from Duke University, CS department, and my colleague Sham Kakade from UW, Computer Science and Engineering department, and Mehran Mesbahi, my other colleague from UW, from the Aeronautics department, expert in control. So a very interdisciplinary group, and yeah, really happy to have had the chance to work with them. So I will look into the problem of the linear quadratic regulator. I'll define it again, but it's the same one that Elad mentioned in a talk earlier today. And we will be looking at, our motivation is to try to understand policy gradient methods, a class of methods that are very popular in reinforcement learning, robotics, etc., but on a very special and very simple problem. And I'll set up the problem, and I'll actually say, why do we want to revisit this well-studied question of linear quadratic regulator? And first, start by looking at a case where we want to solve this problem and have access to exact gradients. Then we look at the case where we don't have access to exact gradients, which corresponds to the case where we don't have the model of the system and still want to control it. Then some related problems that extend this framework. Okay, so the linear quadratic theory essentially is a very classic problem in systems and control, and it deals with the problem of controlling a linear dynamical system. So here's the standard setup. We are looking at this problem in discrete time and infinite horizon. And the dynamics are given by this equation, xt plus 1 equals axt plus but. So here, xt is the state of the system at time t. It's a vector, it can be an Rn. Ut is the input signal, also a vector, at time t. This equation gives the dynamics of the system, which says what the next state will be as a function of the current state and the input. And it depends linearly on the previous states and the input, so it's a linear dynamical system. In the linear quadratic regulator problem, we have this dynamical system, and we want to, the question is this, we want to choose the sequence of inputs, so that's U0, U1, UT, and in infinite horizon case, infinite sequence of inputs, given an initial state x0, in order, so pick the U's, in order to minimize the quadratic cost function of the inputs and the states. That can be written like this, summation of x transpose qx at all times and u transpose r u at all times, where these matrices q and r define our cost function, and they're positive semi-definite matrices, or positive definite for simplicity. Okay, so the problem is this. Given this dynamics, given the initial condition x0, find the optimal sequence of inputs u in order to minimize the cost of the input and the state. Essentially, the goal can be seen as you want to drive the dynamics of the system to state 0, or it could be another desired final state. And you want to find the minimum effort in the L2 cost sense, input to do that. So very classic problem. So we are looking at the infinite horizon case. So this problem has been well studied, and here's the classical solution that you probably have seen in linear dynamical systems courses. So classical solution is basically, it's a dynamic program. You want to solve for every u given, minimize a cost to go function, etc. So you can set up the dynamic program, but because it has linear dynamics, dynamic programming solution for this problem is particularly simple and elegant. It can be solved in closed form via defining an extra variable, which is this P matrix called the Riccati variable. This P matrix has to solve the following equation. It's called the algebraic Riccati equation, or AIR, and it's not a nonlinear equation in P, so P equals this other function that has P in it here, and here, and here. So it's nonlinear equation, but it's an equation in P. If we can solve this equation and find P, which if we know the A and B and Q and R, we actually can, and there are efficient linear algebra-based methods to solve it and iterative methods to solve it, then the problem is solved because we can prove the optimal control is the following. It's going to be the optimal U is going to be a static state feedback, which means a fixed matrix K star times XT. So UT is just proportional to XT. That's optimal among all possible policies. And that this K star, after having solved this Riccati equation, has this explicit closed form in terms of the P and A and B and the R and so on, in terms of the problem parameters, the model, and the solution to the Riccati P. Okay, so nice, solved problem. This is the optimal controller. Another interesting thing is that in this infinite horizon case, the optimal controller is a fixed K star, does not change with time. Whereas in finite horizon, it may change with time and so on. So we're looking at the simpler infinite horizon case. So this is really a cornerstone of much of model-based control. It goes back to Kalman, and actually a lot talked about the history of it. Very interesting history. I won't review that. Recently, there has been a resurgence in studying this problem, particularly motivated by robotics application and trying to connect to some very ad hoc algorithms that are used in the robotics and reinforcement learning context by trying to mimic those algorithms on this problem and see in this simple case, can we prove anything about those? So that has been a big motivation of studying this problem again. For the problem itself, there is extensive theory. There are computational methods for solving this Riccati equation. That goes back to, for example, Kleinman and Loeb in '68, who worked on the continuous time version of this problem, and Hewer in '71, who worked on the discrete case. All of these methods assume you have the A and B and Q and R. All the data is given, you have it, and you can actually plug in and solve this equation. And so all these methods rely on solving for P first, and then finding the optimal control. So here are our questions. In order to, as I said, to motivate connection to reinforcement learning algorithms, we want to see, can we actually solve the LQR problem by algorithms that iterate on the policy? Policy here is the K. So can I actually do a simple update on K? I only use, to make these updates, I only use some information about the cost function as a function of policy. So we define the cost as a function of policy. I'll write down the explicit form later on. And suppose, first, we consider methods that have access to first order, meaning gradient of this cost function, either exactly or approximately. Okay, so that's the first question. Can I build methods that only iterate on the policy and use the gradient of the cost function with respect to policy? Would these methods work? So does gradient descent, even with exact gradient, so suppose the exact gradient with respect to policy is available, would it even converge? If I start gradient descent, would it even converge? If it converges under what assumption? What does it converge to? Does it converge to the global optimal K star, which we know from the Riccati solution? And if it does, what is the rate of convergence in terms of the problem parameters? And then another very interesting thing, actually our goal, is to get to this. What if I did not even have the model of the dynamical system? I didn't have the A and B. And that's sort of model free, where it tries to mimic what people in reinforcement learning call model free. So if gradients are not available, but I have access to sampling the cost as a function of the policy. So I get function value samples. Can I still make progress? Can I still converge to K star? Now, if the problem was convex, this would not be a challenging question. But C as a function of K is not convex. So that's actually one of our main challenges. Why is this interesting? So why are we interested in studying gradient descent directly on K? Because gradient descent directly on K it has its own uses. So for example, it's useful when there are additional constraints on K. One example of which I'll give at the very end of the talk. So even when the model is known, this is still an interesting question because it can allow some extensions to LQR. But also, it can be extended to noisy inexact gradients. So when model is not known, gradients not available, we will show an extension of the analysis. And that once we understand gradient descent, we can consider derivative-free versions, that is, these model-free methods that are similar to policy gradient methods. So basically go from exact gradient to inexact gradient to just function value estimation. So it's interesting. It's like a spectrum from knowing the model to not knowing the model. All right, literature on learning and control. This is a very, very broad area. This is like kind of a sample of many different works in this area. So it's not actually that new. There's a lot of work from the 90s that are very relevant. So Bertsekas and Tsitsikis neurodynamic programming already has looked at problems of whether you know the model or not. How do you do approximate linear programming, dynamic programming? The work of Bradkey for online adaptive control. A lot of work in the literature on adaptive control. Most of the guarantees in adaptive control literature are only asymptotic. They don't actually give finite sample or finite time guarantees. There is so big variety, so I won't go over all of them. And also their goals are different. Some are bounding regret, regret of the prediction of the next state. Some are bounding error of estimation of the optimal control, things like that. So I won't go over all of them, but I want to point out, for example, this work, Hart et al. 2016, is kind of related to what we are doing in the sense that they're actually solving the system identification problem, not control, just learn the system. But they're doing it by gradient descent on a problem that is not convex and showing that with the right assumptions, it converges to the global optimum. In effect, what they're using is actually that under their assumptions, the problem becomes quasi-convex. Very nice work. Another set of works that are related are works from the group of Professor Ben Recht at Berkeley. So this one, for example, takes a different approach to solving the control problem by first doing Fourier system identification up to some epsilon accuracy and then doing robust control for all models that are identified within an uncertainty regime. And as well as a few other work that they did. This second one is related more to like Q-learning, which is a different approach, and more recent work that still also examines model-free and model-based methods for LQR. So there's a large set of works. I also want to mention that Elod's group has done work on this, and Elod talked about it. Some of their work is about identifying a linear or learning linear dynamical system that he gave a talk about earlier. Also very interesting work. And they also have some work about control when the A matrix is symmetric. Seems there's extensions to non-symmetric, which is also very interesting. The goal in these papers, though, it's a bit different. So in the learning paper, the goal is only prediction error, regret bound on prediction error, not the error in learning the system. And yeah, but very interesting, and it would be interesting to explore the connections between these literature. And finally, I want to mention another piece of work that is actually from the controls literature by Anders Ranser and his student. So their work is not about reinforcement learning or anything. It's about the known model case. Model is fully known, but they want to do gradient descent on the controller K because they want to do structured controller design. So there's additional constraints on K, and they do it by gradient descent on K and projection onto those constraints. And it works well in practice, but there is no optimality guarantees. They only do it empirically, and it seems to work well. So that's also another motivation for us to look at these methods coming from a different literature. So these are very varied set of literature, but all very interesting. And I think it's a recent trend to try to connect them better, especially the machine learning side and the control theory side. So, OK, so here's the LQR problem again, and let's set up our problem. Suppose we consider a kind of a simple version of LQR. We do not consider state noise, so it's this model of AXT plus BUT, but we don't, for now, consider any added WT noise. We do consider, however, that the initial condition is random. So I'm starting from initial condition that is randomly drawn from some distribution D. And while it might seem a little bit unusual, it's not that different from actually having a noise right at the beginning, but then not having a noise at every step. So plausibly, we can extend things to having noise at every step too, but seems very messy. So let's stick with this formulation. And let's CK be the cost, the quadratic cost in state and input as a function of the control policy K, and define these two matrices. Sigma K is the state covariance matrix for the infinite horizon problem, so it's a function of a whole trajectory. So for all xt's you're visiting, it's the sum of xt transposes expected value. The expectation is with respect to the randomness in initial condition. And sigma 0 is just the expected value for the first step. So just the covariance of the first initial condition. Now, OK, so that's the notation. We consider the following algorithms. The first algorithm we consider is just, let's do gradient descent on the cost, ck, and update k with a fixed step size eta. Would this work? What should the eta be? And also, we look at a variation of gradient descent that is actually popular in reinforcement learning called natural gradient descent. What natural gradients are, the terminology, for example, comes from Sham Kakad's paper in 2001. The natural gradient is just a gradient that is normalized by the inverse of an appropriate covariance matrix. It sort of just shapes the geometry well. So you can think of it as, yeah, just a little bit like, maybe like quasi-Newton methods, but there is a matrix sigma k, which is the state covariance whose inverse multiplies the gradient. So also, we'll also study that method. OK, so for studying an algorithm, we have to also define what oracle the algorithm has access to. So for the first problem, our oracle is a standard first-order oracle. So gradient of the cost with respect to the policy is available. That's exact gradient oracle. And we also will consider approximate gradient oracle, meaning noisy oracles or no gradient at all, only function values. So this second one, only using function values, is much closer to the 0th order oracle in optimization. So the first one is like first order oracle. Second one is a 0th order oracle in optimization language. OK, so far everything clear? If there are any questions, please feel free to interrupt. All right, so why is this problem hard? Because C as a function of K actually is not convex. Let's first write it down. It's kind of messy, but just to have it in front of us. This is what the CK is. CK is, by the way, expected value of the whole cost with respect to the randomness in X0. And so when we expand it out, it becomes something like this. So the difficulty is that K appears here, and this is a Kronecker product, and this is a big identity matrix, and then there's an inverse, and then you also have a quadratic function of K appearing here, big messy function of K, and definitely not convex. In fact, we came up with a counterexample of dimension, the A matrix being, A and B matrices being of dimension 3, and it clearly is not convex. So we can create counterexamples that show the problem is not convex. In fact, the intuition between the non-convexity is the following. You can have, for example, set A and B to both be identity. You can have a controller K, K1, that stabilizes the system. So CK is a bounded value. And you can have K2 that also stabilizes the system. But their linear combination does not necessarily stabilize the system. And CK can blow up to infinity in between. So it's also related to the fact that the set of stabilizing controllers for a linear system is not convex, and it's a very complicated set. All right, CK is not convex in K. It's also not quasi-convex. We also checked that. For this simple example, dimension 3, not quasi-convex, and not star convex either. So it does not have any nice convex-like properties. In fact, for small dimensions 1 and 2, it is convex, but that's it. Starting from 3, you get counterexamples. So, OK. Let's remember these definitions. Sigma k was the state covariance matrix, and sigma 0 is the initial state covariance matrix. We start by looking at all the stationary points of this problem. So it's a non-convex function, but let's see what all the stationary points are. Where does the gradient become 0? So here's a simple demo. If the gradient of C with respect to k is 0, then one of two things could have happened. Either k is optimal, which is the global k star, global optimal solution, or the covariance matrix sigma k is rank deficient. So basically, there are points that are where the gradient is 0 and they're not optimal, but all of them have this property. All of those non-globally optimal points have this property that covariance of the state at those k's is going to be rank deficient. So this is very helpful because we can actually avoid the second case easily. if I choose the initial state from a distribution that has a covariance matrix that is full rank. Let's say D, the distribution I picked X0 from, has covariance identity, then it wouldn't be an issue because sigma 0 is full rank. So then from then on, any other term that I add, so sigma 0 is the first term in the sum, you add more terms, the rank still remains full. Therefore, all sigma k's are going to be full rank. And the stationary, so this rank deficiency cannot happen. So the only stationary point algorithm actually will reach is going to be the global optimum. So if I'm allowed to assume sigma 0 is full rank, it's easy. We are not going to have any problem with the non-global optimum. So this is helpful because this assumption, in fact, is very reasonable. Just by choosing the initial state randomly, for example, we can satisfy it. So another way to examine this problem, by the way, is actually you can try to transform it into a convex linear matrix inequality. There is a transformation, in fact, that does that. But in fact, the analysis of that is much harder. That mapping is very messy. So we looked at that too. That's probably another alternative way to approach it, but nothing gets simpler. And we find it more easier and more straightforward to just look at all the stationary points of the non-convex function and characterize it. Yes?
Where do we use the covariance K in the cost function? Should we use that at all?
No, sigma k is not, well, it's related to, only sigma 0 is appearing in the cost. So not directly, but it's related. If you write down the expression, sigma k also depends on these kinds of functions. So there's implicit relation between them. Yeah, good question. But I haven't written it in a way that shows. OK, so continuing on looking at the optimization landscape for this problem. Now suppose that sigma 0 is full rank. Then we can show the following. We can show that the function value at k minus the function value at k star is always upper bounded by something times norm of the gradient at k squared. This is a very interesting property. Not too many non-convex functions actually have this property. Functions that have this property are known as gradient-dominated functions. They have appeared in optimization literature often. They have been studied, for example, by Polyak in 60s. However, not many non-convex functions have this property globally with respect to the global minimum k star. This is a very, very special function that has this property. So we can work out and we can show this property. And what does it mean? It means that now if the gradient becomes small, so I'm doing gradient descent, if the norm of the gradient becomes small, I'm guaranteed that I'm approaching the global optimum, right? Because the norm of the gradient is giving an upper bound to the global optimum. Moreover, the rate at which the gradient is becoming small gives me a rate of convergence. So this is very helpful. Again, we are lucky this holds. This does not usually hold for non-convex functions. The coefficients that appear in before also have some sort of interpretation. So sigma k star is the optimum state covariance at the controller, at the optimal controller. So if you apply the optimal controller, look at the whole trajectory, the covariance will be this. Sigma min of the initial covariance matrix and sigma min minimum singular value of the matrix R in the cost. They appear. So this over this is some sort of, you can think of it as a condition number. Sigma max over sigma min related to the state covariance, for example. OK, so usually this property, this gradient-dominated property, is applied together with smoothness of the function to get immediately a convergence rate for gradient-based methods, for gradient descent. But here, our cost function is actually not smooth. And the problem is, in fact, that it blows up to infinity at k's that are not stabilizing. And the shape of this set of stabilizing controllers, which is the domain of definition of CK, is pretty complicated. However, it's not too difficult to deal with this because if we start from a stabilizing controller and iterate, we can show that we are never going to go and hit the boundary. So the controllers along the way are not going to become non-stabilizing. And so using that property, putting it together with the gradient domination property, we get this theorem. This is a rate of convergence for gradient descent in the case that we have exact gradients. So we assume that CK0 is finite, meaning that the initial controller we start from is stabilizing. So that's an assumption we need. You do need to come up with a controller that's stabilizing. However, it can be very far from the optimal controller. Okay? It doesn't need to be close to optimal, but it has to be stabilizing. And we start from initial conditions such that sigma 0 is full rank. And the step size, if the step size is picked in an appropriate way, meaning smaller than some function, I didn't quote it here, and the number of iterations are large enough, we get that the controller generated after n iterations is epsilon close to the optimum, or has cost that is epsilon close to the optimum. So ckn minus ck star is less than or equal to optimum. Now, the number of iterations, which is the rate, is for natural policy gradient algorithm, which was the one with normalized gradients, is given by this expression. The important point here is that the dependence on epsilon or accuracy is log 1 over epsilon. And ck0 minus ck star shows up, which is the initial distance to optimality. So this term is actually pretty good. It's the best we can expect from gradient-based methods. It's the linear rate of convergence. The dependence here in front on all the other problem parameters may not be optimal, but they're reasonable. There are all kinds of things from like condition number of the R matrix that was the cost of the use, and the B matrix, and things like that all appear. For gradient descent, it's a little messier expression. The condition number-like factor is still there. The log 1 over epsilon is still there, as we expect. Again, very good rate in terms of epsilon. And there is a polynomial dependence on everything else, norm A, norm B, norm R, sigma min of A, and not A, sigma min of R, and sigma 0. Similar to this expression, it's a big expression. But it's all polynomial dependence on those. There is room to kind of understand this problem-related parameters a little bit better in these bounds. But we do get both of these algorithms have linear rate of convergence when exact gradients are available. And some simple numerical simulation shows that, yeah, the rate of convergence is good. And in fact, in simulation, we use the backtracking step size, not the fixed step size suggested by the theory. The step size suggested by the theory is a bit small. OK. But we wanted to look at the unknown model case. Unknown model case means I observe xt's, but I have no idea about the matrices A and B. This is closer to what people have in reinforcement learning, model-free methods. OK, so in that case, I can update the k, but I don't have access to the gradient. I can only estimate the gradient. So there's some kind of noisy information about gradient that's available. And same in the natural policy gradient. The sigma k is also not available, only an estimate of it. So we don't know, or we don't directly learn A and B, but we have access. For example, we have, so what kind of information do we have? There are two scenarios that motivates the problem I'm setting up. One is that you have access to a simulator, meaning there is a way to kind of get some sense of the dynamics of the system, but it's a costly thing, so you want to only query it very few times. Or you have ability to explore the system while you're in the physical system by perturbing the controller a little bit. Is there a question?
Yeah.
Yes.
Is there any guarantee that every controller along the sequence will be stabilizing, or can you sometimes get destabilizing controllers?
In the previous case, yes, they're all stabilizing. Yeah, because otherwise TK blows to infinity, and that can't happen. We can actually show. Yeah, good question. Okay. So yeah, so in these cases where you get these kinds of information, it's some sort of partial information about your system, but you do not have a model. So we are going to be using this. We are going to be using the ability to somehow query the system, get some limited information about it, and we'll show the algorithm later. So this is kind of model-free. At least I don't like the terminology model-free, but it mimics that what people are doing in practice. In model-free estimation, what people do is what you do is at the current controller, you perturb this controller a little bit, and you do a rollout, meaning you run the system dynamics for some time, some finite time, and then you look at the state or the trajectory and the cost of this trajectory. And you can also, for example, estimate the covariance of the trajectory, all based on simple rollouts. But from one controller, you can do multiple rollouts, and you do this by adding Gaussian noise. So you perturb around the controller you are by in a random uniform way by adding Gaussian noise. This is also similar to zeroth order derivative-free optimization, where you don't have access to gradients, but you can query the function values, and you query around the point multiple times, and your algorithm moves based on that. So what are the issues? So the issue is, how do you do this query in a good way? How much noise do you add at a current controller? What's the length of the rollouts you have to use? And what's the overall sample complexity, which is like number of rollouts times the length of the rollout? Can we give any theory? So before, there wasn't any theory for this at all, even in this linear dynamical case. So here's an algorithm that we propose. It's very simple. In a sense, there's a lot of room to improve it, but let's first analyze something that is simple. So the controller that we start with is given. And the number of trajectories are m, so we can actually do m rollouts. Rollout length is L. That's the time horizon for each of these rollouts. The parameter of the sampling, this is the order, you can think of it as the Gaussian smoothing parameter, is little r. Dimension is d. OK, so those are the parameters. So how does the algorithm work? For each of the rollouts, what you do is you draw a uniform perturbation. You draw it uniformly and random from all the matrices with Frobenius norm bounded by this parameter r. You add this random matrix to your current matrix k, to the current controller, and you get this guy, k hat I. And then you simulate k hat I for L steps. So you see what the trajectory will be under k hat I for a finite length, starting from some initial condition. And this x0 can now actually be another x that you're at. You can repeatedly do this at different points. Then, getting these rollouts, you calculate the following estimate. So for ith rollout, you get an estimate of the cost and the covariance matrix. And these are finite valued estimates. So it's very crude estimates in some sense of the true cost and the true covariance. Once we calculate this, then we can use these quantities in our gradient descent or natural policy gradient descent algorithm. You just calculate an estimate of the gradient based on these values and an estimate of the covariance matrix based on just averaging the covariances you calculated. So that's a rough algorithm. Now, there are many ways to probably think about better sampling around the point you're at, make use of the properties of the function ck in a better way. This is very simple. It just uniformly probes around. But let's see what we can get with this. So here's the full algorithm about, or theorem about the convergence rate of policy gradient and natural policy gradient to the globally optimal k star in the case that we don't know A and B, but we can run the algorithm I just showed. So for the theorem, we again need to assume that k0 is stabilizing. We start from a stabilizing controller, so ck0 is finite. If step size is chosen appropriately, we can actually say exactly how small it needs to be in terms of problem parameters. And if the number of iterations n, the number of rollouts, the length of each rollout, and the amount of Gaussian noise are all chosen as polynomial function of log 1 over epsilon and all the other problem parameters, which are reasonable choices. Again, the dependence is log 1 over epsilon, which is great, especially number of iterations is again log 1 over epsilon. So it's linear convergence in accuracy epsilon. After n iterations, we get a controller that has epsilon close cost to the optimum. So ck minus ck star is less than epsilon. And the number of iterations, so number of iterations was poly of log 1 over epsilon. Number of samples, so this shouldn't be n, this should be just number of samples. Number of samples is poly in 1 over epsilon. It's a polynomial function of 1 over epsilon and distance to initial distance to optimality, and again, all the problem parameters. So we get optimal dependence on the epsilon, but dependence on problem parameters, all the parameters, are really not sharp, and we didn't really actually aim to make them sharp. So it's a very crude bound in that sense. We are just showing its polynomial could be a high degree polynomial, et cetera. So more careful analysis is needed to show exactly what the degrees are and how the dependence is. So bound is not generally very sharp, but it still shows the polynomial dependence. And it's good on epsilon, sharp on epsilon. So proof sketch for this theorem. Well, so first we fixed the rollout length, and for a fixed rollout length, we have to show that the estimates that we get from this short observation of the trajectory are not too far from infinite horizon trajectory. So first bound the error of finite horizon versus infinite horizon, then show that with enough samples, the algorithm can estimate the gradient and the covariance matrix with the desired accuracy. And then show that the algorithms converge at this rate despite having perturbations or errors in the gradient and or the natural gradient estimates. So you have to combine three different things, three different inexact things. But one can do that and overall get what I said. So this was a summary of the theorem. If you want all the gory details, it looks like this, but I don't want to go through it. So you get things like this. These are the parameter dependence. All the dependence if you wanted to see, but you can look at the paper for more details. Let me skip that. I mentioned also another set of problems that are quite interesting that is not related really to policy gradients, but people in control theory are very interested in. One of them is structured controller design. So suppose you want to design a K that controls a system. Suppose dynamics are known, A and B matrices are known. But you want the controller K to have a specific structure, for example, a specific sparsity pattern, which translates into, for example, if Kij is 0, then it means that edge Ij is not allowed. So for example, the ice controller does not have access to the J's input, something like that. Any kinds of structural pattern constraint on the controller. This also comes up a lot in distributed controller design problems. So along this line, some recent work has been, so this is a known, by the way, known very hard problem in general. In general, it's NP hard. There has been a lot of attempts to work on this. There is a special case of it that is convex, and the special case is actually studied by Sanjay Lal and Laurent Lessard. Under an assumption called quadratic invariance. So if the sparsity pattern on K satisfies a certain assumption, the problem is actually convex. It's a very restrictive assumption, but still good to know that there is a convex special case. Then there is also the work that I mentioned earlier that is empirical, that actually tries and uses gradient descent on the K and projects onto the set of structured controllers, but with no theoretical guarantee. Only empirical, and seems to work very well. So what we would like to do is to use this, the tools that we have to be able to say something about structured controller design using gradient projection, so gradient descent and project onto structure set, and give some theory. This is ongoing work, so I'm not showing any results, but it's possible to, at least for some special cases, we can show some results. So that's another line in which one can continue looking at gradient descent methods in control. Okay, so so I'll conclude. Convergence, so we gave convergence and rates of convergence and sample complexity for gradient descent and its variance, like natural gradient descent. And in our paper, we also have one other variant that's a little more complicated for the linear quadratic regulator problem. Despite it being a non-convex problem, if you look at the cost as a function of the policy, and that this, in a sense, extends to model-free case using sampling of the cost as a function of policy. And these results appeared in our ICML 2018 paper. We're doing more work, and we have some newer work on it that are along the lines of, one of them is the structured controller design that I just mentioned. Very interesting question is also that actually a Lodstock address to some extent is partial state observation or equivalently hidden or latent states. So this is when you don't see fully the xt, but you see yt, which is c times xt. So you see a projection of the state only, not full state. That's an interesting problem. It's a bit hard. It's harder to analyze, but some possible progress can be made. And also, we want to look at different costs. This problem had a quadratic cost function, and a lot of the properties are function of that quadratic cost. But for example, in control, it's very much of interest to look at an H-infinity cost function, which is, for example, for worst case inputs and worst case optimal control or robust control. And that would be very interesting also to work on. And so it opens up actually, I think, the room for looking at nice intersections between machine learning approaches and control theory approaches. And acknowledgement to my collaborators and also some funding. All right. And thank you very much. And any questions? Yes.
So if you went to page 17, you talk about it. So here you're sampling you by time, right? Is there any restriction on it besides the one you did for potential sampling vector that you went for in order?
No, this was very simply sampled from basically a sphere
Is there a chance
uniformly.
you sample with displacement or?
It doesn't really matter in this case. You can even do, yeah, I mean, it's Gaussian sampling, so it doesn't really matter. Gaussian, but with a bound. So, yeah, we actually did not optimize the sampling part. There is some interesting ideas one can probably take from derivative-free optimization, where you use the properties of the function you're trying to minimize to actually pick the samples in a smarter way. We didn't do that. We are doing like kind of like plain vanilla, just uniformly sample.
Sorry, do you mind if I'm asking what's the complexity you're running down?
So here, polynomial in log 1 over epsilon, and other parameters. Yeah, so the full thing is pretty messy. Yeah, like that. That's the runtime. It is still, dependence on epsilon, sorry, there's an epsilon here. Dependence on epsilon is nice. Dependence on other problem parameters possibly can be improved, but we have shown polynomial dependence. So it's at least the first result that shows polynomial. So definitely, I think it's not optimal. I think that there's much room to. Yeah. Other questions? No.
Okay, let's try him again.
Thank you.